Good morning. Myself, Dr.CR kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. So today my main topic is laser glass spectroscopy. In this topic, we are going to discuss about the influence of erbium-3 plus ion concentration and spectroscopic properties of silica borate glasses. This is one of the topic from the laser glass spectroscopy. Next, coming to the laser glass spectroscopy, last and previous session we discussed on the spectroscopic behavior of terbium-3 plus ions in zinc phosphide glasses for green laser applications. So last class session we discussed about the green laser applications we are using for the terbium-3 plus doped zinc phosphide glasses. So in that section we discussed about the introduction, experimental methods and techniques, results and discussion, and conclusion and summary of terbium-3 plus doped phosphide glasses for green laser applications. So today outline of the topic is influence of erbium-3 plus ion concentration and spectroscopic properties of silica borate glasses. In that we are going to discuss about the introduction of the erbium-3 plus ion of the silica borate glasses and experimental methods and techniques of the erbium-3 plus ions, and resultant discussion of the influence of erbium-3 plus ion concentration as well as spectroscopic properties and spectral properties of the silica borate glasses. And finally, we are going to discuss about the summary or conclusion of the erbium-3 plus doped laser silica borate glasses for spectroscopic properties. So in this first introduction, motivation or rare earth elements. So this is the modern periodic table of the complete rare earth elements. Mainly here in the rare earth elements in the lanthanide series, that is starting from cerium to lutetium. So atomic number 58 to 71. So in this lanthanide elements or rare earth elements, today we are going to discuss about the erbium-3 plus ions. That is atomic number 68, atomic volume is 167.3. So today we are going to discuss about the erbium-3 plus doped lanthanide doped glasses in the silica borate glasses. So in the importance of lanthanides, what are the importance involved in the lanthanum-3 plus ions, especially in the erbium-3 plus ions? So this is the complete rare earth ions or lanthanide ions from lanthanum to lutetium, that is from ground state level, from the ground state level to xenon into 4FN configuration. This is F2F transition of the lanthanide ions. So lanthanide ions important properties is first shielding of 4F orbitals, similar chemical properties and electrostatic bonding and variable geometry of the erbium-3 plus ions in the case of erbium-3 plus ion. In the case of lanthanide ions, especially we are going to discuss about the erbium-3 plus ions. So what are the fascinating optical properties of the important parameters involved in the importance of the lanthanum-3 plus ions? So luminescence from FF2 transition, because this erbium-3 plus ions belongs to the F black elements, that is F black orbital, that is erbium-3 plus ions. So characteristic emission for each rare earth ion as narrow emission lines, high chromatography purity, and emission color is not very dependent on ion's environment, large Stokes shifts, and direct excitation in 4F levels is not efficient, and sensitization luminescence is prepared, and long excited state lifetimes. These are the fascinating optical properties of lanthanum-3 plus ions or rare earth elements in the specifically in the case of erbium-3 plus ions. That is the erbium-3 plus ions of the. Today we are going to discuss about the what are the influence while doping of concentration of erbium-3 plus ions, how spectroscopic property will be changing in the host material of silica borate glasses, that we are going to study in this topic. So this is the different emission spectra of the rare earth elements. That is, this is first one is thulium, terbium, dysprosium, europium, samarium. These are the visible emissions and nearly 450 nanometer to 680 nanometers. This is the Ni region elements, that is yttrium, neodymium, erbium. These are the, so in our case erbium is nearly we can get the 1531 nanometer, that is 1531 nanometer of the near infrared emission we can get, that is useful for the NIR laser applications we can use for the erbium 3 plus dope silica borate classes that we are going to study in this topic. First, coming to the main introduction of the rare earth elements, that is 4f and 5f black elements and their unique trivalent state 4fn electronic shielding by 5s to 5p6 electron. This is the outermost erbium 3 plus electron configuration. It covers in the 5s to 5p6 electrons in the 4f electron shielding. And so many advantages involved in the erbium 3 plus science. What are the glass's importance? So glass is an indispensable photonic platform material due to its high optical transparency and thermomechanical strength and the ability to be shaped into an almost unlimited range of geometrical structure and composition. We can prepare the glasses from bulk glasses to like fiber drying also. So in the case of glasses, that is the important unique applications in the glass materials. What are the important applications involved here? So laser gain media, one of the important application. Next, fiber amplifiers. So we can use for the glass material as a fiber amplifiers and optical components we can use, and medical accessories, different kind of medical accessories made by the glass materials only. Next, massive structure and entertainment, etc. These are the different kind of applications on the glass materials. Next, whenever the rare earth elements doped in glasses, what kind of applications is importance parameter we can calculate or use to study in the case of rare earth elements. That is many applications. That is mainly laser gain media is one of the important parameter while rare earth elements doped into the glasses. Next, optical fiber amplifiers. So these are the important applications involved in the rare earth elements doped in the glass materials. So these are the importance of the rare earth elements. Now this main introduction on the rare earth elements of the erbium 3 plus science. In recent years, there has been a unique applications in the field of optical communication, and tremendous amount of research work has been carried out in the study of luminescent properties of rare earth elements doped glass materials. Since of the good glass forming ability and wide variety of applications in various rare earth doped oxide glass hosts such as silicates, borates and phosphates and tellurates have been synthesized and published. So that is references 1 and 2. Among the various oxide classes, borate glasses have attracted much attention because of their electrochemical and optical applications, namely as solid state lasers, optical waveguides and luminescent materials. Borate glass is a particularly suitable optical material because of its high transparency, relatively low melting point and high thermal stability, different coordination number and good rare earth ion solubility. These are the important parameter involved in the oxide based glasses. In the case of erbium 3 plus doped glasses, fibers have large potential for their use in the wideband internet because of inhomogeneous broadening for erbium ions in glass matrix. So telecommunication, that is a broadband applications we can use for the erbium 3 plus doped laser glasses. So these are the one of the unique applications in the, particularly in the case of erbium 3 plus doped glasses can use for the telecommunication application purpose, that is the internet. Nowadays we are using 5G, 6G. These are mainly involved in the erbium 3 plus doped glass fibers only. Therefore, a great attention has been devoted to the research on erbium doped fiber amplifiers, EDFA. That is erbium doped fiber amplifiers is the key element in wavelength division multiplexing WDM systems, near infrared telecommunication windows, eye-safe laser systems and LiDAR transmitters. These are the different applications involved in the research oriented erbium 3 plus doped silica borate glasses. Next, coming to the material selection. So in this topic, we are present material selection highlights the fact or advantages behind the selection of borate glass systems for the present study. Next, In this present study, we have discussed about the influence of erbium 3 plus ion concentration on spectroscopic properties of silica borate glasses. What are the chemical composition involved in the erbium 3 plus doped gadolinium, calcium, silica borate glasses? Here we use it in the gadolinium and calcium. So here chemical composition of the present study usually is the 55 minus X mole percentage of boron trioxide B2O3. Next 10 mole percent of silicon dioxide. Next 25 mole percent of gallium oxide. Next 10 mole percent of calcium oxide. And X mole percentage of impurity or rarest elements, that is erbium Er2 both this is dopant. We are using X mole percent of erbium oxide, that is starting from X equal to 0 mole percentage to 0.5, 1 mole, 1.5, 2.0 mole and 2.5 mole percentage of erbium 3 plus ions, starting from low concentration 0.5 to 2.5 mole percentage of erbium 3 plus doped gadolinium, calcium, silica borate glasses prepared by using these chemical compositions. So hereafter refer each and every glass composition. BSGD CA ER00 means that is undoped one, 0 mole percent of erbium, that is host material without dopant. Next with dopant of less concentration of 0.5, 1.0, 1.5, 2.0, 2.5 mole percent of erbium 3 plus ions in the silica, gadolinium, calcium, silica borate glasses. Next coming to the experimental technique. So glass prepared by the conventional melt quenching techniques. So mainly glasses, all the glasses prepared by the unique technique is called conventional melt quenching technique. Initially above mentioned chemical composition, we have to take weight of the 20 grams. By using to optical balance, you have to measure the 20 grams of each batch composition. Total weight is 20 grams of all the chemicals. Next, after that, taking that all chemical, we have put into the agate mortar. We have to crush that is a micro size powder to very fine nano size powder. We have to crush like fine powder by using the agate mortar. That is by using grind of thoroughly. Next, after taking the grinded powder, you put into a platinum crucible and covered with platinum lid. So after that platinum crucible, you are insert into the electrical furnace at the melting temperature of 1004 degrees centigrade. Temperature duration of time is 90 minutes. That means 1.5 hour duration. We need to use the electrical furnace at the temperature of 1400 degrees centigrade. After melting the glass composition, we need to pour into the preheated brass mold. That is quenched from 1400 degrees centigrade to room temperature. We need to quench in the preheated brass mold. After that, we can keep into the annealing. That means annealing means we have to heat at annealing temperature is 460 degrees centigrade. Time duration is 5 hours. Why? What is the purpose of annealing? Is to avoid the thermal stress and strain. So any air cracks, to avoid that cracks, we need to keep into the preheated brass mold at the temperature of 460 degrees centigrade for 5 hours. After annealing completed from 460 degrees centigrade to room temperature, we need to, by use the polishing or cutting, we have to use this one. After fine polished glass sample, we need to measure for the, initially we need to measure for calibration purpose. First calibration technique, we need to measure first is XRD, X-ray diffraction profile. By using the X-ray diffraction profile, we need to whether it is glassy sample or crystalline sample. We need to whether it is confirmed by using the XRD profile. So finally, we are getting in this XRD profile, we are getting all the peaks are broad peaks. That means it shows the completely glassy nature. There is no crystalline peaks. That is why it can be. Finally, we are concluded that so prepared glass sample are the completely shows the glassy nature of the materials. So this is the erbium 3 plus doped silica borate glasses preparation techniques. Next, coming to the characterization methods. So experimental technique or characterization methods. First, initially we need to measure the absorption spectra. So absorption spectra, we need to measure the Flickr Link spectrometer. That is spectrometer model number is lambda 950 in the wavelength range of 250 nanometer to 2500 nanometers. After absorption spectra, we need to measure fluorescence and decay time measurements. That is emission spectra and lifetime measurements in the case of visible as well as near infrared emission, that means NIR, visible region and near infrared emission. So the spectra were carried out with a FLS 980 spectrometer by exciting 379 nanometer in the visible region and a Xenon arc lamp with a spectral resolution of 1 nanometer and 980 nanometer is near infrared region. So emission spectra and lifetime measurements we are measuring. In the case of visible region, we need to excite by using the 379 nanometer. If you want to measure the near infrared region, you need to excite by using the 980 nanometer laser diode with a spectral resolution of 1 nanometer and incident power of 650 milliwatt. So these are the fluorescence and decay time measurements. How to measure? Next, NIR decay times were measured by exciting the sample with 980 nanometer laser diode. Output power P is 650 milliwatt with frequency of 100 Hz with a indium gallium arsenide detector was using and digital oscilloscope. You need to measure the decay time measurements. So these are the fluorescence and decay time measurements. So all the measurements were carried out by at room temperature only. So you need observation spectra and fluorescence and lifetime measurements. Each and every measurements was carried out at room temperature only. So these are the characterization technique of the erbium-3 plus dope silica borate glasses. Next, coming to the resultant discussion. Initially, we need to study the optical absorption spectrum. So here shows the optical absorption spectrum from UV visible as well as near infrared region. It's starting from 350 nanometer to 1800 nanometer. So x-axis wavelength versus absorption coefficient in the alpha is centimeter inverse. So erbium-3 plus ions ground state energy is quarter I 15 by 2. Quarter I 15 by 2 different excited states from quarter G 11 by 2 and WG 9 by 2 and quarter F 15. These are the different visible region absorption bands and near infrared region starting from 1400 nanometer. This is the we are getting quarter I 13 by. This is the important emission in the erbium doped silica borate glasses in the range of near infrared region. That is the 1531 nanometer. This is the important emission band in the erbium-3 plus doped glasses. That is why we are using for the telecommunication applications. We are using for the erbium-3 plus doped laser glasses. So this is the figure shows the optical absorption spectra of 0.0 mole percent. This is 0. That is low concentration of 0.0 mole percentage of erbium-3 plus doped in gadolinium calcium silica borate glasses. So this is UV visible near infrared region. This consists of 9 bands we are observed due to the transition from the ground state quarter I 15 by 2 the various excited state levels from quarter I 13 by 2 different states. Among the 9 absorption transitions, the 6 absorption transitions are well resolved to the calculate the oscillator strength and their energies. So by using this absorption bands, we are taking 6 absorption bands. By using that one, we are calculating, that means here 1, 2, 3, 4, 5, 6. So this is among these 6 absorption bands we need to calculate the oscillator strength of the absorption spectrum. Next, coming to the optical absorption spectra. So in this oscillators, by using the oscillator strength Fx min F100, we are calculating the Judah of rate intensity parameters. That is the omega 2, omega 4, omega 6. In the present study of 0.1 mole percent erbium-3 plus doped silica borate glasses, we are getting the omega 2 value is 3.16 into 10 power minus 20 centimeter square. Omega 4 is 1.32 into 10 power minus 20 centimeter square. Omega 6 is 0.99 into 10 power minus 20 centimeter. Here the trend is follows: omega 2 is greater than 2, omega 4 greater than 2, omega 6. That means the trending omega 2 value is more compared to omega 4 and omega 6. The larger value of omega 2 parameter in the gadolinium calcium silica borate glasses indicates the higher degree of covalence between the erbium-3 plus ions as well as ligands surrounded by the erbium-3 plus, that is oxygen, O2 minus ions. These are ligands. These are the important because the omega 2 parameter having the highest value, highest degree, that means 3.16 into 10 power minus 2 compared to omega 4 or omega 6. That is why this indicates that the higher degree of covalence between the erbium-3 plus ions and its surrounding ligands, that is oxygen, O2 minus ions. So these are we are getting information from the absorption spectrum. So these are the excitation spectra of the erbium-3 plus dope gadolinium, calcium, silica borate glasses. This figure shows the from 6x 7 by 2 to 6 at 15 by 2 gadolinium peak. This is due to the gadolinium because in our host material we are using the chemical composition 25 mole percent of gadolinium. That is why you are observing the impurity of the gadolinium 3 plus ion. That is belongs to 8s 7 by 2 to 6i 15 by 2 transition. So remaining are the erbium 3 plus ion transitions. So this figure displays the excitation spectra in the wavelength range of 250 to 530 nanometer in the erbium 3 plus dope, gadolinium, calcium, silica borate glasses. This 275 transition belongs to the gadolinium 3 plus. In the other 6 transitions are associated with the erbium 3 plus ions from 2G7 by 2 different transitions. This wavelength corresponding to the prominent excitation band can give the intense emission. So this is the we are going to use the for emission spectrum analysis. We are going to use for the excitation spectrum. So this is the visible emission of the erbium 3 plus dope, gadolinium, calcium, silica borate glasses. The UV excited emission spectra by exciting with 379 nanometer for different concentration from 0.1 mole percentage to 2.5 mole percentage by exciting with 379 nanometer. We are observing three important visible emissions from 2H 11 by 2 to 4 15 by 2 transition. This is one transition in the wavelength range from 480 nanometer to 520. Yes, 520 to 570 nanometer belongs to 4 3 by 2 quarter. This is green emission. 4 3 by 2 to 4 15 by 2 transition. This is green emission. This we are getting from the 545 nanometer around. Next 580 to 600 nanometer we are getting the 4 9 by 2 to 4 15 by 2 transition. This is the nearly red region. So intense green emission we are observing in the visible spectra, while erbium 3 plus dope, gadolinium, calcium, silica borate glasses. See, among with these two green emissions, a red emission peak 570 nanometers bands corresponds to these transitions. So these are useful for the green laser applications also suitably we can use for the erbium 3 plus dope laser glasses. Next, coming to the emission spectrum analysis. So here this emission spectrum SLJ energy parameters we are going to calculate by using the emission data, visible emission data. By using the visible emission data, we are going to calculate the orbital tension probability, next branching ratio, and radiative tension lifetime, decay time, radiative decay time, that is T tau R. So these are we are calculating, and emission cross section we are calculating by using the formula of lambda 4p by 8 pi nc square delta lambda effective, that is full width of measure by using we are calculating, and the branching ratio we are calculating area under the absorption curve, that is area under the emission curve in there. While using the emission spectrum analysis, we are calculating the different radiative properties delta E and AR, BR and tau R. These are the radiative properties of the erbium 3 plus dope, gadolinium, calcium, silica borate glasses. Next, coming to the visible decay time lifetime measurements. So in this lifetime measurements, we are taking the in figure shows the portraits 3 by 2 level of the glass, that means green laser emission. So green laser emission we are exciting with 379 nanometer. We are observing 550 nanometer of the emission of the visible region of erbium 3 plus dope, gadolinium, calcium, silica borate glasses. So low concentration lifetime we are getting 9.43 millisecond, that is microseconds, by using this formula tau experimental integral of t into I of t dt by integral of I of dt. By using this formula fitting with the single exponential nature, we can calculate the erbium 3 plus ions lifetime measurements from low concentration to high concentration. Here see the concentration increases, lifetime measurement decreasing from 9.43 microsecond to 6.80 microseconds. So increasing the concentration, visible decay times are decreasing due to the energy transfer parameter involved in the erbium 3 plus ions doped gadolinium, calcium, silica borate glasses. See, all the glasses visible decay curves are exhibits non-exponential nature. The experimental lifetime tau experimental is calculated by using this formula. So this curves finding the average lifetime using the formula shown below. So by using this formula, we are calculating the lifetime measurements of the all the concentration of the erbium 3 plus ions. This is increasing the concentration. Lifetimes are decreasing from 9.43 microseconds to 6.80 microseconds. These are the visible decay time measurements of the erbium 3 plus doped, gadolinium, calcium, silica borate classes. Next, coming to the NIR emission, that means near infrared emission spectra. So far we studied visible emission spectra as well as visible decay time measurements. Now we are going to discuss about the near infrared emission spectra. So near infrared emission spectra, we are using the excitation wavelength is 980 nanometer. That is quarter 13 by 2, quarter 15 by transition of the erbium 3 plus dope, gadolinium, calcium, silica borate classes, different concentration. The insert figure shows the variation of integrated intensity function of the erbium 3 plus ion concentration. Here, concentration versus integrated intensity of the different concentration from 0.5 to 2.5. So increasing the concentration, the integrated intensity of the erbium 3 plus ion in the near infrared, that is 1531 nanometer, that intensity will be increasing. While increasing the concentration, that integrated intensity also increasing. That is mainly due to the concentration pinching of the erbium 3 plus ions. See here, the emission intensity increases with increasing of erbium 3 plus ion concentration and is shown in the insert figure. It can be seen that the near infrared emission peak position located at 1531 nanometer. So this is the quarter 13 by 2, whatever. So it's slightly shifting will be takes place. This the nanometer shifting from 1531 nanometer to 1571 nanometer with increase in the erbium ion concentration. It is worth noting that the gadolinium, calcium, doped silica borate classes is lambda p showed the red shift, that means here 40 nanometer compared to erbium 3 plus 0.5 mole percentage. So here red shift, that means blue shift means if you have the low region it will be shifting, means that will be the blue shift. Now this low concentration to high concentration, it will be shifting from red region, that is upper level, the upper region, that is nearly approximately 40 nanometer compared to low concentration of erbium 3 plus dope, gadolinium, calcium, silica borate. So this shows that there is a chance to red shift. That means wavelength will be shifting to red region, the higher wavelength region. If lower wavelength region means blue shift. So here in this case we are observing the red shift. That is why the wavelength will be shifting. That is around 40 nanometer compared to low concentration of erbium 3 plus dope, gadolinium, calcium, silica borate classes. Next, coming to the NIR decay time measurements of the erbium 3 plus dope, gadolinium, calcium, silica borate classes. Here time versus normalized intensity, we are exciting the 980 nanometer, but emission monitoring at 1531 nanometer. From concentration from 0.5 mole percentage to 2.5 mole percentage. These are the lifetime measurements. Also, here low concentration 1.46 milliseconds and 1.41 1 mole concentration. 1.5 is 1.38, and low higher concentration of the erbium 3 plus ions having the lifetime is 1.35 milliseconds. So in the case of visible region, at a monitoring at the green emission 550 nanometer, we are observing the lifetime in the visible region is microseconds. But in the case of near infrared measurements, we are getting the milliseconds. So lifetime will be longer lifetime. We are observing the near infrared region. So the shortening of lifetimes of the quarter 13 by 2 level is higher erbium 3 plus ion concentrations were likely due to the enhancement of non-radiative energy transfer process through energy diffusion. So that is nearly decreasing from 1.46 millisecond to 1.35 while increasing the erbium 3 plus ion concentration. That is why this is mainly due to the enhancement of the non-radiative energy transfer process through energy diffusion. That is why that emission transition pitching will be takes place. That is why lifetime measurements will be decreasing from 1.46 nanometer to 1.35 milliseconds, increasing of erbium 3 plus concentration. This is the near infrared decay time measurements of the erbium 3 plus dope, gadolinium, calcium, silica borate classes. Next, coming to the partial energy level diagram of erbium 3 plus ions in erbium 3 plus dope, gadolinium, calcium, silica borate classes. See, this is the energy level diagram from erbium 3 plus ion from ground state, quartile 15 by 2, different excited state levels. Instead, you are exciting the visible region 370 nanometer. We are getting the green emissions, two green emissions and lower intensity, and green emission is at this 550 nanometer. We are getting the intense green emission at 550 nanometer. So low intensity is 506 nanometer and red emission at 591 nanometer. So among the three emissions, we are observing in the visible region 550 nanometer is the maximum intensity. That is why this erbium 3 plus doped glasses we can use for the green laser applications. Also we can use for the in the case of visible region. So erbium 3 plus dope is one of the important application. Next, while studying the near infrared region, so we are pumping with 980 nanometer. We are getting the near infrared emission is 1531 nanometer. This is the intense emission in the near infrared region. That is why 1531 nanometer. This is mainly useful for the telecommunication applications and fiber amplifiers also we can use for the erbium-3 plus doped aluminum calcium silica borate glasses. So these are the energy transfer mainly takes place due to the cross relaxation channels. That cross relaxation channels is mainly a quartile 3 by 2, quartile 15 by 2 to quartile 13 by 2, quartile 9 by 2. This is one of the transition. Next other one is a quartile 13 by 2, quartile 15 by 2 to quartile 9 by 2, quartile 13 by 2. This is other transition. These two cross relaxation channels is involved in the energy transfer parameters. That is why this is the mainly this lifetime measurements and intensity will be decreasing while increasing the concentration. That is mainly due to the cross relaxation channels. That is diffusion type of the method here involved in the erbium-3 plus dope gadolinium calcium silica borate glasses. These two channels causes the two nearby interacting erbium-3 plus ions, one excited at the quartile 3 by the visible region channel emitting level and the other one is quartile 15 by 2. That is ground level. These are the involved in the energy level diagram of the erbium-3 plus ions in gadolinium calcium silica borate glasses. Next, coming to the conclusion or summary of the present topic is the influence of erbium-3 plus ion concentration on spectroscopic properties of silica borate glasses prepared by conventional melt quenching technique, and it was studied by using the absorption, excitation, visible and near infrared emission as well as decay time measurements visible as well as near infrared regions. Next, a relatively higher value of omega 2 value is we are observing is 3.3 into 10 power minus 20 centimeter square. That is mainly due to the higher covalency and higher asymmetry around the erbium-3 plus ion in the present host material. That is one of the important conclusion. Next, the full width of maximum FWHM value varies from 75 nanometer to 106 nanometer with increasing the erbium-3 plus ion concentration from lower concentration 0.5 mole to 2.5 mole per are the emission wavelength of 1531 nanometer. That is the maximum full width of maximum value are found at 106 nanometer for the higher concentration of 2.5 mole per of erbium-3 plus ions. Next, full width of maximum value and stimulated emission cross section sigma value and figure of merit sigma emission tau experimental and decay times value of the quartile 13 by 2, quartile 15 by 30, 1531 nanometer transition of the present 0.5 mole percent of erbium-3 plus doped glasses found to be 75 nanometer. That is full width of maximum value and emission cross section value 5.10 in 10 power minus 21 centimeter square and figure of merit value is 7.43 into 10 power minus 24 centimeter square into seconds and lifetime measurements of the 0.4 moles percentage of the erbium-3 doped glass is 1.46 milliseconds. So finally hence the erbium-3 plus doped gadolinium calcium silica borate glasses may be promising host for the development of lasers and broadband optical amplifiers at the wavelength of 1.5 micrometer. This is 1.5 micrometer window telecommunication systems. We can use it because we are getting a near infrared emission is 1531 nanometer. So this is why around 1.53 micrometer. So this wavelength we can use for the telecommunication application purpose. This window region we can usually for the erbium-3 plus doped gadolinium calcium silica borate. This is highly useful for the optical fiber amplifiers applications and near infrared laser applications also we can use for the erbium-3 plus doped silica borate glasses. These are the one of the important application in the case of erbium-3 plus doped glasses. So finally references. So these are the important references covered by this topic. So in this paper we can in this complete topic was published in the year 2016 in the one of the important journal of alloys and compounds. This is the one of the important journal we are published in the influence of erbium concentration and spectroscopic properties of gadolinium calcium silica borate glasses. So these are the important references involved in the present topic. So thank you. Next class will be continuing in the next section.
Like, share and subscribe. Hit the bell icon for more updates.